Alright, here we are back again for part 4, an unexpected surprise video. The last one took a little longer. Let's finish things up here. So we finished on this question and we had done all of that. We found out how to solve this and we found out a great shortcut on our calculator that does that for us. Let's take a look at the last one now then and see if we can use that same calculator shortcut to help us out. So this one says find the probability that x will be greater than or equal to 3 but less than 6. So that means we're looking for x values that are 3, 4, and 5 because 3 is included but 6 is not. So 3, 4, and 5. So again, we are looking for what is the probability that you will get 3 questions right, 4 questions right, or 5 questions right if you're purely choosing randomly your answers to those questions. So let's take a look. One way to take a look at this is to say, well, that probability is the same as between 3 and 5, including 3, including 5. So notice how this has just been rewritten like this, and we've done less than or equal to 5 here instead of the 6 here. Okay, that can be further written like this, and this is kind of the big and important logical step in this one, that when we are looking for the numbers 3, 4, and 5, we can say basically it's the probability of it being less than 5 minus the probability of it being less than 2. Because if you say probability of it being less than 5, you're saying, sorry, less than or equal to 5, you're saying it can be 5, 4, 3, 2, 1, or 0. But since we only want 3, 4, and 5, we don't want all the way from 5 down to 0, we want only 5 down to 3, so we subtract away the values of x less than 2, because that would be 2, 1, and 0. So it's like we have 5, 4, 3, 2, 1, 0 here, and we subtract 2, 1, and 0 here, and we're left with 5, 4, and 3. So think about that for a moment and see if it makes sense. But now that we know that, we can just do that on our calculator, right? And the good news is this problem already set you up. We already have this value here. It's the one we calculated in B, so it's the one we just got here. So to find the answer to this question, we can just punch this on our calculator and subtract the one we just did a moment ago. So just a reminder how to do this on our calculator. You're going to turn it on and press second vars, which is distribution, arrow up until you see binomial. And again, since we're looking for x values less than or equal to 5, we know we have to use CDF because we need to do multiple variable values for that x, not just a single value but several, so cumulative CDF. Okay, so there 6 trials, 0.25 is our probability. We're looking for 5 or under, so I'm going to put 5 here, and then paste, enter. So enter again, and there's our answer. That's the probability of getting 5 or under correct. Notice that's a really high probability. That's like a 99.9% chance. That makes sense. What's the chance you'll get 5 or under correct? That means what's the chance you'll get 5 correct, or 4, or 3, or 2, or 1, or 0? Well, that's a very high chance, because all that does not count is getting all 6 correct, which is super unlikely when you're guessing. So that makes sense. But then remember, we take that number minus the probability of less than or equal to 2, which we got here, 0.831, enter, and there's our final answer. So about a 17% chance of getting 3, 4, or 5 correct. So there's our answer. I think it should be here. There it is. Okay, great. So let's go on to the next one here. In the previous lesson we did part A. Now we're going to look at parts B, C, and D in this question as well. In this question, it doesn't have the description here of what you have to do, but first you have to figure out if it is binomial distribution, because we can't use these shortcuts in this formula on the calculator unless we know we've confirmed that this is a binomial distribution. And I'll just point out a couple things. A binomial distribution, we need to know how many trials there are, and we also need to have like a constant probability. Like in the last one, it was a constant probability of 1 in 4, or 0.25, that you would get a question right if you guessed, and that was the same, right? It didn't matter if you got the last question right or wrong. The next question you still have a 25% chance of getting the right answer. So that probability is independent, right? So if there's ever dependent probability, it's not binomial and you can't do it. So take a look at B. Okay, in B, let's see if we can set it up. So we have this variable x. Well, I guess it shouldn't be x here. It should be, they call it b. So I really should have a variable b. But anyway, x is distributed binomially. And in here, we're picking 5 chocolates. So there's 5 trials. And the chance of getting a dark chocolate is 7 chocolates out of a total of 19 chocolates, because you add those up. So 7 out of 19 is your chance of getting dark chocolate. Then we can continue, right, and set up the probability statement, right? Probability of getting 4 dark chocolates, and then it's 5 selections of chocolate, 4 of them are dark. There's our chance of getting a dark, so 4 of those, 1 of those of not getting a dark. But before we punch this all in our calculator, let's think about it. It turns out this one is not binomial. Why? Because it says when you grab a chocolate from here, you note what chocolate you got, and then you eat the chocolate. Alright, so when you eat the chocolate, next time you go to grab a chocolate, you will no longer have 19 chocolates. You have 18 left. And if you grab the dark one, then you only have 6 out of 18 dark chocolate left. So all of a sudden this probability, or this one here, is not constant. And therefore we cannot use these formulas. It doesn't work. This relies on a constant probability. So therefore this is not binomial, because trials should be independent. There shouldn't be dependent probability. Therefore we can't do that, and it's not binomial, so we can't solve this. We leave this question unsolved. Okay? Alright, let's look at C. In C, read it out, okay. Okay, in C we have these dice, and there's a blue one and yellow and red, and we're trying to select a... We grab one die from this pile 12 times, and we're trying to see how many yellow dice we get. And we're trying to find the probability that we've gotten 6 or fewer yellow. 6 or fewer yellow in 12 draws of the dice. Okay, so this time the color is distributed binomially, with 12 being your number of trials, because we're going to repeat this thing 12 times, and then 7 out of 18. So is that the probability of getting a yellow? Well, there's 7 yellow, and altogether there's, 18 dice. So that's the chance of getting a yellow one. And it does say that every time you grab a die, you note the color and then you replace it, so you put it back in this pile. So the pile is always reset, and we always have this probability of getting a yellow in that case. So this time it is binomial, and we can run the probability. So probability of getting yellow, choosing yellow 6 or fewer times. That means what's the chance of getting 6 yellows out of 12, or 5 out of 12, or 4 out of 12, or 3, or 2, or 1, or 0. So all those numbers, what's the chance of getting all those numbers of yellow out of 12 experiments, or 12 trials? So that you can punch in your calculator, and using the whole binomial thing we were looking at. Alright, so I'm going to do it one last time. Second, vars, then I'm going to arrow up to binomial. Is this CDF or PDF? Well, this one is definitely CDF, because we're looking for a cumulative 6 and under, so all those different values of C. Enter number of trials, 12, and then probability 7 divided by 18. And the value we're looking for is 6 or under, so I'm going to put 6 here and paste it. Enter, enter again. We have a probability of 0.86. Wow, that's very high, 86%. Let's see if that matches. Yep, 0.86 right there. Very strong chance of getting 6 or fewer yellow dice when you run this experiment 12 times. Great, okay, so try D now. Okay, in D, we're again stuck with a problem, and the problem is this. This person's playing lottery, and every time the probability of getting a winning ticket is that. So that's set. Doesn't matter if you got a winning ticket the last ticket or not. The probability of your next one being a winning one is always 0.001. So that probability is independent, it's set. So that's great. But here, question mark, we don't know how many trials we're running here. It does say we want to find out what's the chance this person gets less than 7 winning tickets, but less than 7 winning tickets out of how many tries, right? It doesn't say, do they buy 20 tickets? And then we want to see what's the chance they got 7 or fewer winning tickets, or do they buy 30? We don't know. It doesn't say. It doesn't tell us the number of trials, so that's a mystery. Therefore, again, we cannot run a binomial distribution on this. We can't get the probability that way, so let's leave that one be like that. Okay, so next one here, we looked at the first part of this problem, which is AI, and that was what's the probability of getting of having 3 girls in a 6-child family. So this one was explained already, but again, here's the number of paths. 6 choose 3 tells us, I think that will give us a result of 10. So there are 10 paths in the tree diagram that lead to 3 girls, 3 boys. Okay, let's look at part 2 now. The probability exactly 3 consecutive girls are born. This one's a little different than expected maybe. Let's take a look how we set it up. So 3 consecutive girls means something like that. So first baby, second, third baby, 3 girls in a row, and then 3 boys. Okay, another way to have 3 consecutive girls is a boy first, and then 3 girls and 2 boys, right? Or 2 boys and 3 girls, right? And or 3 boys, and then the last 3 kids are 3 girls. Those are the only 4 ways to get 3 consecutive girls born in this family. But now, how do we proceed? So this question is a little bit out of the box thinking, because we're not going to do this whole thing here. We're not going to use this shortcut on the calculator. What we have to say is, well, there's 4 ways, and then what's the probability of each of those things, right? What's the probability of having girl, 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 boy, boy, boy? Well, the probability of having a girl is 0.5. We assume that the probability of male-female is equal, 50-50, right? So this is like 0.5 times 0.5, 0.5, 0.5, and then boy, 0.5. So what we really have is probability of 3 consecutive girls is 4 of these arrangements, but each of those arrangements has this probability, 0.5 times 0.5, 0.5, 6 of them. Imagine a tree diagram. It would be like girl, 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 and then boy, boy, boy. And that path is always 0.5 multiplied 6 times. And then we have 4 different paths that lead to 3 consecutive girls. So multiply those, and we get an answer of this. So that's the chance of having 3 consecutive girls. That's a good problem. Let's look at part B here now. So question B. Please read that out and see if you can set that up. This one is tricky, I'll tell you. This one's quite tricky. So give it a try, and then I'll explain how it's done. Okay, here is the process for this one. A study shows that 0.9 of the population of over 4 million carries the virus. Okay, so we have the probability of a person being a virus carrier. It says, find the smallest sample from the population. So now it's saying a sample means how many people they have to take from the population, so that the probability of having no carriers is less than 0.4. So it's giving you the probability that will be calculated, but it's not telling you how big the sample is. In other words, it's not telling you how many people to take, which means it's not telling you how many trials are being run, because you can consider taking, each time you take a person from the population, it's like 1 trial. Okay, so 1 person, 1 person, 1 person. It doesn't say how many. We want to see what's the smallest number of trials we can take. So here's our binomial distribution. We have virus carriers are distributed binomially. We have an unknown number of trials, and we have a probability of this, that 0.9% turns into 0.009 as a decimal. That is the probability of having a virus carrier. So we're going to set it up. So we need probability that we have 0 virus carriers, because that's what this is saying. We want a sample with no carriers, so 0 virus carriers. So let's set it up. We have a combination. We have some sample. We don't know how big it's going to be, but that's what we're solving for. And we're selecting 0 virus carriers. We want to know how many ways is there to get 0 carriers. And then here, so this is a carrier, probability of somebody being a carrier of the virus, and we want 0 carriers. And then 1 minus this number is this value here, right? Because if this was 20%, this would be 80. If this was 70, this is 30. They always combine to make 1. So 1 minus this is this. And that is the number of non-carriers, and we don't know how many it is, but it's going to be the number of the sample here. Okay, so in combinations, anything choose 0 is equal to 1. And then anything here, anything to the power 0 is also 1. So those both turn into 1, and we're left with this. That equation can be simplified to this, because those 1s multiply. Now we're left with this, and this can be solved on our calculator. How about we begin there next time, I'll show you how to do this on your calculator, how to get this answer. Meanwhile, you're done both videos. Please try the practice assignment before our next lesson. See you soon.